Now it is time to begin the one-way ANOVA. A one-way ANOVA, remember, has one factor with at least two independent levels. So here's an example of that. Researchers want to test a new anti-anxiety medication. They split participants into three conditions, 0 milligrams, 50 milligrams, and 100 milligrams, then asked them to rate their anxiety on a scale of 1 to 10. Are there any differences between the three conditions using an alpha of 0.05? So here are the three conditions. There are 7 people in each condition, and there are their scores. So we're going to do an ANOVA using these 7 steps. And I've already gone over this a few times, so I'm just going to go right through it. First is stating the null and alternative hypotheses. Now in an ANOVA, our null is that the three groups are equal to one another, and the alternative is that not all the groups are equal. That's it. Our alpha level is what I said it would be, 0.05. Just use whatever is stated, 0.01, 0.05, whatever. In this case, we're using 0.05. Next, we're going to calculate the degrees of freedom, and we're going to need 3 of those. We're going to need degrees of freedom between, degrees of freedom within, and degrees of freedom total. Now, before I do that, we need to make sure you understand the distinction between capital N and lowercase n. Lowercase n in this case is 7. It refers to how many people are in each level of the independent variable. And capital N refers to the total number of people in the experiment. So lowercase n is 7, capital N is 21. We're going to use that to calculate the degrees of freedom and some other things. So these are the equations for the degrees of freedom. You see we have n, we have a, we have 1. A refers to how many levels of the factor that you have. So in this case, we have 3 levels, 0, 50, and 100. So A is 3. So that makes our degrees of freedom between 2, our degrees of freedom within 18, and degrees of freedom total 20. Notice that total is just between plus within. 2 plus 18 equals 20. If between plus within don't equal total, that means something went wrong. Next, we will state our decision rule. To look up the critical value we need to use 2 different degrees of freedom. We're going to use degrees of freedom between and degrees of freedom within. We're going to use 2 and 18. Now we're going to use this F table, which looks very complicated. Hopefully you're watching this in high definition so you can actually read what these numbers are. This is the smallest F table I could get into this lecture. But this is the F table. On the top we have the between groups degrees of freedom, and on the left side we have the within groups degrees of freedom. So I'm going to use between is 2 and within is 18. And that's how I'm going to find the critical value of 3.5546. So our decision rule is, if f is greater than 3.5546, we're going to reject the null hypothesis. Next, we need to actually calculate the f. So this is an f table, an ANOVA printout table, and what we're going to do is we're going to use this table to find f, the area that I have indicated in red. The whole thing we're doing right now, the whole point of this is to calculate a single f value, which we're going to compare to the critical value. So I'm going to put in the degrees of freedom that we already know, 2, 18, and 20. And next we're going to calculate the sum of squares. We're going to need sum of squares between, sum of squares within, and sum of squares total. This is the equation for sum of squares between. Now most of it makes sense, except for that weird sum of ai squared thing. Really what that means is you're going to take the sum of each level, square it, and then add those together. It'd be easier for me to show you, which I'm going to do. You're going to take the sum of each of the 3 groups. You're going to get 57, 47, 21. You're going to square each of those sums, and then you're going to add together all of those sums. That's what that means. So hopefully if you're good with that, you should be good with this whole equation. Now t squared, well t just refers to the total sum. So if you add all the numbers together, if you add together 57, 47, and 21, you get a t of 125. And we already know lowercase n and capital N. We know that they're 7 and 21. So we can find sum of squares between. If we solve for it, we get 98.67. Next, let's do sum of squares within. Sum of squares within is sum of all y squared minus, hey, this thing, we already found it when we were calculating sum of squares between. We already know the second half of this. We already have that, so we can just plug that right in. We just need to find sum of all y squared. What that means is you have to square every individual value and then add them all together. So our sum of y squared is 853. That's the first part of this equation. So now solving for sum of squares within, we get 10.29. And lastly, we have sum of squares total. Now the nice thing about this is both parts of it, the sum of y squared and t squared divided by n, we already found both of those. We can just put in what we found before. And we find a sum of squares total of 108.95. So let me go back to this ANOVA table. I'm going to put in our three sum of squares. Now we're actually almost done. We're very close to finding the f. Now the f, in order to find it, it's just ms between divided by ms within. That means mean square. So mean square between divided by mean square within. We just have to find those two things. And if we have those, we have f. Now these are the equations for mean square between and mean square within. All you have to do is take the sum of squares and divide it by the degrees of freedom. So like to find mean square between, you just take 98.67 and divide by 2 and get 49.34. Same thing within, you just take 10.29 divided by 18 and get 0.57. And now that you have both of those mean squares, you can just divide them to find an f. And we get an f of 86.56. Now everything we've done so far, it was just to get that f. And now we're going to go back to our decision rule, which was if f is greater than 3.5546, reject the null hypothesis. We found an f of 86.56, so that means we are going to reject the null hypothesis. Our conclusion in this case would be the three conditions differed significantly on anxiety level. And then the official way of writing that would be f218 equals 86.56, p less than 0.05. Now we just know that the groups are different somehow. We don't know where they're different. To actually figure that out, we would have to do a post hoc test. But from this one-way ANOVA, we did discover that there is a difference somewhere among these three groups. And that is a one-way ANOVA.